Welcome to podcast 2 of the video podcast series in chemistry. This is unit 10 and we're dealing with nuclear chemistry. The learning standards that we're dealing with in this particular podcast will be 10-4, which has to do with binding energy. So welcome. I'm going to look at binding energy. Learning standard 10-4 simply says this: I can explain how proton-proton repulsion in the nucleus is overcome, and this is overcome by the nuclear binding energy. I can calculate the mass defect of the nucleus, quantify the binding energy using the equation E equals mc squared, and relate how the binding energy per nucleon can be used to predict nuclear stability, which is the resistance to disintegration. When we talk about binding energy, there's going to be what we call requisite knowledge. There are 4 fundamental forces in the universe that produce interactions between objects or particles. The first of these is gravity, and gravity affects all particles. It is only an attractive force. It's the weakest of the 4 fundamental forces, but it can act over a great distance. The second of the 4 fundamental forces we're going to look at is the electromagnetic force. An electromagnetic force acts between electrical charges and magnetic fields and is responsible for all physical and chemical processes. It acts over large distances and can be either an attractive or a repulsive force depending on the charge of the individual particles that are interacting. The third fundamental force in the universe is the weak nuclear force. This is limited in distance to the nucleus and causes unstable particles and nuclei to decay. And finally, the fourth fundamental force in the universe is the strong nuclear force. It is also limited in distance to the nucleus, and it binds quarks into nucleons. Remember, nucleons are protons and neutrons, and nucleons into the nuclei. It's what holds the nucleus together. If we understand what the 4 fundamental forces are, we can look at binding energy. Now, binding energy is going to be responsible for the strong nuclear force that holds the protons, that keeps them from repelling each other away in the nucleus, and that holds the nucleus together. So for binding energy, except for the hydrogen 1 nucleus, which has just 1 proton in it, no neutrons, all nuclei are a combination of protons and neutrons. The positive charge on the protons is responsible for repulsion. Remember that like charges repel, opposite charges attract. The force that holds the nucleus together is generated by nuclear binding energy. Binding energy is the amount of energy required to hold the nucleus together. It is also the amount of energy required to decompose a nucleus or to break it apart into its individual nucleons. Mass defect is the difference between the sum of the masses of the nuclear components, which are protons and neutrons, and the actual mass of the corresponding nucleus. The sum of the masses of the nuclear components is predicted. We know the mass of an individual proton and individual neutron. We add those together, and then we look at the actual mass of the nucleus. There's a difference, and this is called the mass defect, and we'll do a calculation together that will show you how we arrive at that. But the difference in mass, much of that lost mass is converted into binding energy, and that's what we're going to use to calculate, in fact, the quantity of binding energy. And really the only rational way to do that at this level is to assume that all of the lost mass was converted into binding energy, and that's an assumption we will make. The best way to talk about mass defect and binding energy is to do a problem. So here is a sample problem. My recommendation for you is that with each of the slides as we work through this sample problem, that you pause the podcast and write down the problem, write down the steps that we're using, so that when you get similar problems in class, you'll be able to solve them following this same template. So our sample problem simply is this: Calculate the binding energy in joules per nucleon of the nucleus of an atom of iron 56. The observed mass, that word observed will often actually use the word experimental mass, or actual mass is used sometimes in place of observed. But the observed mass of one atom is 55.9349 atomic mass units. Well, we have an atom, iron 56, which is an isotope of iron, and we need to find its binding energy per nucleon. So our first step is to use the periodic table to determine the atomic number, Z, of iron, and the number of neutrons, which is the mass number A minus the atomic number Z. So iron 56 has an atomic number, Z, of equal to 26, so there are 26 protons. Then the mass number A is 56, so A minus Z is equal to 56 minus 26, and that gives us 30 neutrons in the nucleus, and we need to know that. Once we know the total number of protons and the total number of neutrons, we can move on to step 2. And here we're going to determine the predicted mass, which is sometimes called the rest mass, of the nucleus based on the sum of the masses of the individual nucleons. For the mass of protons, we're going to take the 26 protons times the mass of one proton, 1.00728 atomic mass units, over the one proton per proton. When we do that, we get the mass of protons is 26.18928 atomic mass units. The mass of neutrons is equal to 30 neutrons times 1.00867 atomic mass units per neutron, and that gives us a mass of neutrons of 30.2601 atomic mass units. In case you're wondering where we got the mass of a proton, mass of a neutron, that was given to you earlier in the course. You could certainly look it up in any textbook. You can look it up online at an educational website, or in any handbook of chemistry and physics. So that's where we get that. It's a known mass. Now our predicted mass, we add the mass of the protons and the mass of the neutrons together. So 26.18928 atomic mass units plus 30.2601 atomic mass units for the neutrons gives us a predicted mass of iron 56 to be 56.44938 atomic mass units. Once we have the predicted mass, or the rest mass, we can move on to step 3, which is to calculate the mass defect of the iron 56 nucleus. The mass defect is equal to our predicted mass minus the actual mass, or observed mass. So our predicted mass minus the actual mass is equal to 56.44938 atomic mass units minus 55.9349 atomic mass units, which gives us 0.51448 atomic mass units. Our mass defect is 0.51448 atomic mass units. We're now ready to move on to the next step. We want to take the mass defect and we want to change that mass that's in atomic mass units into kilograms, because in order to use the E equals mc squared, we need to have the mass in kilograms. So one atomic mass unit is equal in mass to 1.66 times 10 to the negative 27th kilograms. So we want to convert the mass from atomic mass units to kilograms, and I want to give you a hint. You want to set up a ratio or proportion and solve for the unknown by rearranging the equation. And when you set up your proportion or ratio, set your unknown on top in the ratio, and it makes rearranging the equation much simpler. So here, the unit I'm going to is kilograms, so I'm going to put my x kilograms on top over 0.51448 atomic mass units, and I set that up equal to 1.66 times 10 to the negative 27th kilograms over 1 atomic mass unit. Continuing with step 4, I'm going to rearrange the equation so that I can isolate x kilograms by itself. And the way that I'm going to do this is I'm going to multiply both sides by the 0.51448 atomic mass units. This will isolate x and provide the final equation to solve for the x value of the kilograms. So I multiply both sides by 0.51448 atomic mass units. When I do that, On the right-hand side, you'll notice that 0.51448 atomic mass units will cancel out on top and bottom, and you'll be left with x kilograms by itself. So that will leave us with the final equation that allows us to solve for x. So I'm ready to solve for x. I have my equation set up, 0.51448 atomic mass units times the factor of 1.66 times 10 to the negative 27th kilograms divided by 1 atomic mass unit will equal x kilograms. Notice that in this equation the units AMU, atomic mass units, will cancel. You're left with kilograms as a unit, which is what we were trying to find, and it's a way of checking yourself to see if you set the equation up correctly. If the proper unit canceling leaves you at the end of the problem with the unit you're looking for, the likelihood is that you set the equation up correctly. So the AMUs cancel, we're left with kilograms. We multiply across the top, 0.51448 atomic mass units times 1.66 times 10 to the negative 27th kilograms divided by 1 AMU will give us 8.54 times 10 to the negative 28th kilograms. So our mass defect in kilograms is 8.54 times 10 to the negative 28th kilograms. You may be thinking to yourself, that's a lot of work to calculate binding energy. And it may seem so, but this is how it's done. If you're going to engage chemistry at any level, the complexity of these types of problems will become the norm for you. So gird yourself up for this type of problem, because as we go through the year, you'll see more and more problems of this level of complexity. So we're ready to move on to step 5. And what we want to do is we want to calculate the total binding energy using the equation E equals mc squared. That's the famous equation that was derived by Albert Einstein. E is the energy in joules, m is the mass in kilograms, and c is the speed of light. And the speed of light is 3 times 10 to the 8th meters per second. So I want to set this equation up and plug my numbers in. E equals mc squared is my base equation. So I put my mass, 8.54 times 10 to the negative 28 kilograms, times the speed of light squared, so 3 times 10 to the 8th meters per second squared. And when I do that, I get 7.69 times 10 to the negative 11th kilograms times a meter squared per second squared. Now, you'll notice that none of the units in this problem cancel. Okay, nothing cancels out, so you have to multiply and divide the units you have. And the units, kilograms times meter squared per second squared, have been simplified by chemists and physicists into what we call a derived unit called the joule. And joule is the proper unit for energy that's used throughout most of the world. So our total binding energy is 7.69 times 10 to the negative 11th joules. Well, we're almost to the end of this problem. The problem asks for the binding energy per nucleon. We have the total binding energy. We need to divide by the number of nucleons in the nucleus to get the binding energy per nucleon. So here's the equation, total binding energy in joules divided by the number of nucleons. So it's 7.69 times 10 to the negative 11 joules divided by the 56 nucleons in this iron 56 nucleus. Remember that the number of nucleons is equal to the mass number. And when we do that, we get 1.37 times 10 to the negative 12th joules per nucleon. We have the binding energy in joules per nucleon, but it's kind of a bulky number. To the negative 12th is a difficult number to conceive of. So oftentimes binding energy is expressed in what's called a mega electron volt. And a mega electron volt, which is symbolized by a capital M eV, is equal to 1 million, or 1 times 10 to the 6 electron volts. So 1 mega electron volt is equal to 1.6 times 10 to the negative 13th joules. So what we want to do is convert our joules per nucleon to mega electron volts per nucleon. So to do this conversion, we're going to set up a proportion that relates the mega electron volts to the joule, And you can see it's very similar to how we did our last proportion. We put the value we're trying to find on top. So we have X mega electron volts over 1.37 times 10 to the negative 12th joules. And we set that equal to the quality of 1 mega electron volt over 1.6 times 10 to the negative 13th joules. Our next step is to multiply both sides by 1.37 times 10 to the negative 12 joules. When we do that, they'll cancel on the right side, which will allow us to isolate X mega electron volts by itself. So that's our goal, is to cancel units on the right side so that we have an equation that solves for X mega electron volts. Well, we continue on, making sure that we cancel the 1.37 times 10 to the negative 12 joules from the right side of the equation, top and bottom. And when we do that, we're left with 1.37 times 10 to the negative 12 joules times 1 mega electron volt over 1.6 times 10 to the negative 13 joules. Our joules will cancel. We'll be left with mega electron volts, which means that we set this problem up correctly. And all we have to do now is take our 1.37 times 10 to the negative 12th, multiply that by 1, which very happily is 1.37 times 10 to the negative 12th, and divide that by what's on the bottom, 1.6 times 10 to the negative 13th. When we do that, the number of mega electron volts in 1.37 times 10 to the negative 12 joules is 8.58 mega electron volts. So there are 8.58 mega electron volts of energy per nucleon of iron 56. Well, that 8.58 mega electron volts of energy per nucleon of iron 56 is a very high nuclear binding energy per nucleon. It is a very stable nucleus in nature, and on the next slide you're going to see a chart that relates nuclear binding energy per nucleon versus mass number. And there's a graph that can be also very helpful to you that's found at a website that I have listed on this slide. And it would really be good if you went to that website, because they have an excellent discussion of this topic. But on the next slide you're going to see a graph of binding energy per nucleon versus mass number. And here's the graph that we referred to, the binding energy per nucleon in mega electron volts versus mass number. Notice the very high binding energy per nucleon for helium. You can see that if you look at where it almost looks like an EKG pattern, jump and fall there at the very left side of the graph. And then notice that iron 56 is right up at the very highest area of the binding energy per nucleon. It peaks at right about iron 56 through 58 in terms of mass number, and then you see that the binding energy per nucleon begins to go down after that, and the heavier the mass number, it shows that trend going down. And it's one of the reasons that reveals that the heavier nuclei are less stable and tend to have more radioactive decay processes in order to get them to a more stable state. So there it is. Well, this is the end of podcast 2 of Unit 10 having to do with nuclear chemistry. I want to leave you with a quote by the esteemed English novelist Jane Austen. "General benevolence, but not general friendship, made a man what he ought to be." I wish you well.